So I usually don't work, in fact, I don't work on common envelopes. So I don't know if what I'm going to present today has particular relevance. But it's an interesting physics issue that my colleagues and I have been thinking about. Whether the issue is whether it's possible to have a negative dynamical friction on black holes which are moving through dense medium. So this is a cartoon of a conventional Bondi-Hoyle accretion flow, where you have an object, a compact object, which is moving to the left. So I'm considering this problem in the frame of reference of the compact object. So the compact object here is at rest, and the streamlines are going from left to right. And then the streamlines are bent by the gravity of this object. They collide somewhere behind. They form an overdensity. And this overdensity exerts gravitational pull onto this compact object, and so pulling it backwards relative to its motion. Okay, and many people, including people in this room, have investigated this. Now, on the other hand, if you don't have an object which is gravitating strongly, but instead is a strong source of wind and moving supersonically through the gas, and this wind will collide with the incoming gas flow and will form a bow shock. Okay? And you can see immediately the basic idea is that behind the bow shock there is an underdensity, and all of the dense gas is either ahead of the moving object or concentrated in the shell, in the mass shell, which corresponds to the bow shock. So let's look at this picture a little bit more. So this is the only calculation that we did. Which is to consider a particular solution of the bow shock, which was found by Wilkin in '96. And this solution is found in an approximation where the temperature here is zero. So this is a zero temperature approximation, means that the two gas flows, when they collide, they stick to each other. However, the momentum within this shell is conserved, so it's an honest solution in terms of physics. And so there are two, I mean, it's an idealized physics, but it's an honest physics. So there are three components of gravity, right? One component comes from the gas which is ahead of this shell. The other component is the shell itself, and the third component is the wind. So you can take a Wilkin solution, you can analytically find the gravitational force which is acting on this compact object, and you find that there are three regimes. So the first regime is, so this is V star is the velocity of the flow relative to this compact object. In other words, it's velocity of the compact object moving through the gas. And then there is V wind, okay? So when V star is smaller than V wind, the friction is given by this expression, right? And it's actually negative, so it's pointing in the direction of the motion of so the object accelerates. But not intuitively, when we started, we didn't know that this was going to happen. But when V star actually is faster than, significantly faster than V wind, this bow shock bends sufficiently that the gravity from the shell actually overcomes the gravity of the material ahead of it. So the friction becomes normal. Okay, the friction is backwards. So that's the two regimes. And the crossover happens at about this value. Okay, so this is an analytical solution. This is the only honest calculation which goes into our paper. Okay, so then what follows is hand waving and speculation. But here we follow a very noble tradition in terms of hand waving and speculation. So this is a paper, which is an amazing paper, actually, by the way. If you haven't read this paper, then I highly recommend that you read this paper. This is a paper about observational appearance of black holes. So these two guys just thought, what's going to happen if black holes accrete a bunch of gas? What are possible observational appearances? Okay, so you read in the abstract that if there is, you can read the outflowing matter, blah, blah. Supercritical regime of accretion of black hole may appear as a bright, hot optical star with strong outflow of matter. This is the abstract. And this is in the body of the paper. In consequence, at a supercritical regime of accretion, the black hole may appear as hot optical star. And so there is a strong mass outflow with this velocity. They actually give an expression of velocity. I tried to understand the origin of this alpha, I couldn't. But I understand all the other scalings that they have here. And the basic picture that Shakur and Sunyaev have is that, okay, you have some supply of gas at a super Eddington rate. There is, it's far enough that you can still form a nice thin accretion disk, but at some radius, the photons become trapped, so the disk cannot cool anymore efficiently, so it becomes quasi-spherical, and then in order to keep accreting, it has to shed some mass. And the amount of mass that you shed is basically everything. So you have only a small fraction which accretes here onto the black hole. But it is this accretion, because accretion is so effective in releasing energy, it is this accretion which is ultimately the source of the wind, and the wind is indeed given by this kind of expression. Okay? Now, this is the prediction in 1973. In 1976, there is a catalog of H-alpha emission stars in the Milky Way, which is published by Stephenson and Sadilek, two astronomers in Case Western University, S and S, right? And this is object number 433. So this is SS433. They found a bright optical star with H-alpha emission, so pretty amazing. Now, of course, we know that this is now a standard candidate, standard object of black hole which accretes the super Eddington rate. And I would say, if you read through all the observers' papers and reviews, the basic, summary of it is that the original idea and original scalings of Shakur and Sunyaev are confirmed. So this object, in the wind, you have something like 100,000 times the Eddington accretion rate on the black hole at scale. The wind velocity is about 1,500 kilometers per second, and they can actually probe different directions because the disk is precessing by an angle of 20 degrees, so you have different angles of views. You also have jets, and jets can serve basically as a colorimeter of amount of stuff that goes through the horizon. So by measuring the power in the jets, you do see that only a small fraction of this m dot actually gets to the black hole here. Okay, and one remarkable thing is that people have been measuring this 13.1 days orbital period, and it hasn't changed over the last 40 years, even with this huge accretion rate. So, no, I think it's a remarkable system, and not everything is understood about it. Now, in terms of scaling for the wind, this is what we use. Basically, we normalize to what is known about SS433 for all of our estimates. Okay, so the basic picture, and this is like hand waving, is that you have a black hole which moves through the dense gas, and so some part of this gas accretes, some fraction of the Monty-Hall accretion rate goes into this thin disk, and then you have a massive outflow coming from the inner edges of the disk, a massive wind, and creates a bow shock in the rest of the gas. Whether this configuration actually happens or not, I don't know. It's one possibility. You can also have possibility where you have limit cycles, where you have periods of accretion which fill the disk, and then the rest of the time the disk blows the wind and creates a bubble. So this condition that the velocity of the wind is greater than the velocity of the black hole moving through gas gives you this type of condition on density. Okay, the interesting parameter here is eta. Eta is a fraction of the Bondi-Hall accretion rate which supplies the disk here. And we know from Morgan's work that eta can actually be substantially less than 1, even in the limit where you don't have feedback. If you have feedback, it may be even less still. So nonetheless, these are characteristic densities of the outer envelope, okay, of the stuff. Okay, so the claim is that at densities which are smaller than this value, this picture should work and you should have negative dynamical friction. This is to be tested, obviously, by numerical experiment. Okay, so what happens if you have higher densities is even less sure, because there are no, unlike, if you call Shakur-Sunyaev solution, it's a good solution, even though it has never been really confirmed by numerical experiments. What happens at higher accretion rate, where this wind is compressed, is even less clear. But there is a very interesting paper by Eric Kachlin and Mitch Begelman in 2015. This is a so-called zebra solution. So these guys were thinking exactly about the situation where the outflow is suppressed by the inflow. So in particular, if you have something like a TDE, and the radius of circularization is smaller than the radius of the sphericalization of the disk. So then they say, basically you form a quasi-static star around the black hole, and this star processes m dot in such a way that most of it gets to the black hole. And then the accretion of black hole drive jets that puncture the star. And basically, they say it's a huge ejection machine, right? So they wanted to explain some of the jets that are seen from tidal disruption events. So if this is correct, then this is probably great for this idea of negative dynamical frictions, because jets are, first of all, very fast, certainly much faster than the motion of the object through the gas, and they probably inflate large bubbles outside of the Bondi radius. So this is exactly what you need to clear that area behind the end of a moving object. So I would say that there is currently no existing numerical experiments confirming this zebra solution. Okay, so this is my last slide. In terms of common envelope, I think it's a possibility, and I want to, in this case, comment on Natasha's objection that there is nothing special about the case where you have strong feedback. If you do have some kind of negative friction, then there is a reason why a compact object would park itself on the outside layers, because clearly when a compact object is way outside the star, then the friction is positive. If the claim that when it's inside the star the friction is negative is correct, then it will tend to park itself always next to the surface layer. So in this case, indeed, the peeling of the envelope would proceed in layers and probably more gradually than the estimates that people here are making. Okay, and an interesting possibility is in fact that SS433 is an object which is currently in this machine. That's all.
Just a short comment on your last point. I think it's quite surprising that SS433 is in this phase for such a long time. I would have expected to go into common envelope phase a long time ago.
So you agree that there is something special about SS433?
Yeah, I'm agreeing with you. Yes.
Another comment?
Yeah, I wonder what's your views on this formation in this environment. I mean, it is clear that there's certainly net angle momentum, even in the case where also you're transferring weight and creating binaries. But I think as Morgan showed, and Eric's work also has shown that cooling is essential in order to form a disk in those equations. And my concern has always been that inside a common envelope at these rates, it's hard to find an effective coolant. I mean, for your case in SS43, it's not clear to me that if you're highly super Eddington, then this formation will be easy to do. But
well, it's certainly something that should be investigated. I thought Morgan simulations formed the disk around the compact.
So we see rotation, but stuff tends to sort of circulate once and then get swept downstream when Ariadne put tracer particles into the flow.
But we still have like 1% of the Bondi which gets into
so gas is getting in there, but it's never rotationally supported in a sort of structure that's orbiting multiple times. And so I think it'll be really interesting to ask, what is the MHD of that sort of thing where you're sort of constantly sweeping it out? Like, can you amplify fields in the ways that we think are important to these outflows? I think it's not at all obvious. I think another thing that'll be, and this is really wonderful to think about, but I think it'll be really interesting to think about how this interacts with the sort of shape of the spherical shape of the star, where there's a preferential direction for the bubble to expand in, which is sort of outward to where there's less obstacle. So I think you'll probably get really interesting and morphologies in that case, and maybe shift some of the criteria.
I agree. Of course, all of our arguments are for pure like infinite medium with some angle.
No, but that's the place to start. But presumably, there's some transformation there as you go more towards a less uniform environment, then the bubble distorts.
If you're at the edge, if you're hovering at the edge, more, you're a little bit farther out. plunge deep in, on the edge. Just at the edge.
Right, so that's why.
Yeah, but if it plunges too fast, well, then you end up in really quenched.
Yeah, the outflow is quenched, so you have to accrete it to a black hole, and you have jet.
Yes, but yeah. So, but right, it depends on. That's right.
What if the outflow is jet?
If
I mean, that's what you're referring to.
Yeah, if you fall in.
I would say quenching of the outflow is boost formation of the jets, because traditional, like, ethnicity of the field, like I said, the power in the jet is very small compared to the envelope.
I mean, quenching the jet, quenching, I mean, if you're the secondary, well, okay.
I think what he's referring to, and I think Adam brought this point, is that the initial onset of common envelope at this formation, and cooling may be very efficient, and then jets will be produced. But if you plunge in dynamically, then cooling will not be as effective, and you adding a degree of freedom in the vertical direction. And what we see in the simulations is that unless you have a fairly compressible equation of state, you don't form a centrifugally supported structure in which the MRI can grow over many orbits.
You have to relieve the pressure somehow, from the ambient pressure to which those fluid lines are just
Okay, so thank you, Yuri, and then the next talk is by Adam, right? We're going to talk about planetary nebula by CE. Okay. Okay, 2 minute one.
So thank you to all the organizers for this great meeting, which has learned a huge amount. So what I want to talk about today, at Rochester, we're interested in common envelope for a lot of different reasons. But we came into it sort of with the interest in planetary nebula shaping. And this is an old question, and I want to go through this. And I want to show you some new work that we're about to publish in collaboration with Ursula's group. So these are just the team that we're working with. So originally this first work was done by Joe in collaboration with Ursula and her student Thomas. Now Amy Zhao has taken it over. So the question is planetary nebula, which have a wide variety of shapes, but really most of them are bipolar, right? Actually, there's very few planetary that are actually spherical. It's a really vanishingly small amount. And the more, when we see spherical, they're really usually, they're cylindrical and we're seeing them way down the waist. But the important thing is that there's a whole class of planetary nebula that are really very jet-like, or they're bipolar, and they have these wasp-waisted ones, where there's really the very narrow waist. And then also, as you can see, there's an amazing degree, when if you look through blurry eyes, they look very symmetrical. You have these nice symmetrical lobes, but as your resolution increases, they're not symmetrical at all. And there's this beautiful case of OH231, where the lobes are actually completely different size. So that's been something, as we've been going through understanding planetary nebula. First, we wanted to understand the bipolar shapes, then the fact that they weren't just bipolar, sometimes they were very jet-like, and then the fact that, as we saw with clearer eyes, that there was a lot of asymmetry.
Can I ask just, sorry.
Sure.
I mean, is it clear that this is an intrinsic asymmetry as opposed to like the ISM density is higher?
Yeah, you see it. I mean, it's pretty intrinsic in the sense. You see it across so many different cases. Also very internal, right? It's not just at the edges. It's also, you see this asymmetry in blobs that are very deep in the lobes themselves. So this idea, this is one of the things I just want to impress upon you, which for me is very exciting. This idea of shaping of planetary nebula by common envelope goes way back. In the 80s, it's people like Noam and Mario Livio and Mark Morris. And, oh, look, if you have a binary, they're going to eject mass preferentially in the orbital plane. And, then if you drive a wind into it, you'll be able to do some shaping. And this is paper that Vincent Ecke, this was when I was a graduate student, did, showing that actually you could get very strong collimation out of having a donut of gas around, that you first eject a donut, probably from the binary, then you'd have a fast wind from the whatever interior sphere there, and you can see this actually shows a simulation where you get it's very old, right? We were like, yay, 128 by 128 resolution, and you can see that the donut was controlled by some ad hoc density function. Here it looks much more like a cored apple. This is the ejecta, and you drive a wind into that, and you would get a jet. And one of the important things about the jet was, there's always a two-shock structure with this. You drive a wind into an environment, and you get an outer shock expanding outward, sweeping up the ambient medium. And then there's an internal shock which is where the wind is being decelerated. And if it becomes elliptical, then because it's an oblique shock, material from the free expanding wind hits it and is redirected into a jet stream. So we were very excited about this paper that Harold Melleman and I did just after we got our PhDs. We spent a lot of time, so Q here is the ratio between the mass in the pole and the mass in the equator of the ambient medium. And as you see, as Q increases, 3, 7, 14, 30, you first of all get something that's much more jet-like, but also it's hard to see here, but you're getting a more elliptical inner shock. And we spent an enormous amount of time in this paper trying to figure out the hydrodynamics of that. So this is the background. We've been thinking about this for a long time, and what's remarkable now with common envelope evolution is we are actually able to get this, right? This was ad hoc, this density distribution, and I want to show you now the consequences. And this paper that I'm about to show you, which is, we're just finishing up, is, it's very much a physics experiment, but it captures the essence of what we think of what's going on. And what we're doing is we're starting from a simulation, an SPH simulation that Ursula and Thomas did. Here is the density distribution. You see the size scales, on the order of 400 AU. Starting off with a 0.8 mass red giant, a 0.39 core of that, a 0.6 mass companion, and the final separation ends up at 20 should be stellar or solar radii. What you see is you get this big extended envelope. You also get some, because the evolution is going on, they've let this run for a while, that the ejecta is expanding. But the important thing to see here is this very dense torus in here. So what we're going to do is we're going to take this SPH simulation, allow our AMR code AstroBear to digest it, run it for a little bit longer, and then right at the center there in a little sphere, we're going to inject a spherical wind. Yes?
You're doing this in
3D.
With the 3D SPH initial.
Yeah, so we're taking the 3D SPH initial condition and then bring it into the 3D AMR. So there was quite a bit of work that Joe had to do in order to get the code to be able to accept this. We're going to do 4 runs, a high momentum case and a low momentum case for the wind, right, for the spherical wind. Now, of course, so the common envelope evolution is completely self-consistent, right? But now what's not self-consistent is we're just going to add at the, in the beginning of our simulations, a spherical wind that is either going to have high or low momentum, meaning mass loss rate, a high case is going to be 10 to the minus 4, low case is going to be 10 to the minus 5. In all cases, the wind speed is going to be 300 kilometers per second, which is about appropriate for the escape velocity of, of this. Maybe the binary merged. Maybe you've got one of the binary or the primary or secondary producing a wind. We're not asking. That's a black box for these simulations. We're also going to see what happens with radiative cooling in the outflow or not radiative cooling. In general, we would expect radiative cooling to occur in these cases, but it was important just to sort of get a sense of how these outflows work. So we can talk about the initial conditions more if anybody's interested. Given the time, I'd like to go right on to the simulation. So this is our case of high momentum, no radiative cooling. The white outline here, or the white contour shows is coming from the temperature, really shows you the outline of the outflow. And you can see, first of all, the most amazing thing is from this little teeny tiny, condition there where we're driving the wind, you get these beautifully highly collimated outflows, okay? So this is, I think, about 3,000 days approximately of evolution. And you see two important things. One is beautiful amount of collimation, becoming somewhat self-similar in the sense that the shape is not really changing in terms of the aspect ratio, but you do see asymmetry between top and bottom, right? The flow that's happening here is not the same as the flow that's happening there. So that's already an important thing to understand, that the nature of since the common envelope, what was left from the common envelope wasn't symmetric, we don't expect the outflows that we're driving to be symmetric, even though we're driving a symmetric wind, right? It's a fully spherical wind. The temperature tells the story of some very interesting hydrodynamics happening here. So the temperature, what you're seeing here is at the top of the lobes, material that has been shocked as it sweeps up the ambient medium. So very high temperatures there, as you'd expect. But notice also these elliptical, highly elliptical shaped regions of lower temperature. Basically what you're getting here, and we're going to see as we go to the end, that you're getting, down here, the wind the spherical wind is being redirected into a jet which has some opening angle, and as it expands, it cools, and then when it runs into this material here, it's shocked again. So you're getting sort of multiple redirecting shocks in these flows, which is something that really, in some sense, we had already seen or predicted back with those very low resolution simulations back in '96. This is the case of low momentum and no cooling. And what you see here is similar to what's happening before, but if you look carefully, you'll notice the southern lobe is not as extended as the northern lobe, and there's quite a bit more asymmetry between top and bottom. So in this case, in the low momentum case, the outflow has a harder time pushing through the chord apple, right? So the common envelope distribution, really, it's like a very narrow nozzle that you're driving the spherical wind into. And the wind is sensitive to any inhomogeneities or top-bottom asymmetries that were imposed just by the chaotic nature of the common envelope evolution, and you see that reflected in the outflow. So there's more asymmetry in these simula in the low momentum case there is in the high momentum case. So as you imagine, as you crank down for even lower momentum case, you'd have, it's possible that you get just, one lobe emerging, or one lobe emerging in a very different way. Now, if we add cooling, what is happening with the radiative? So when we talk about cooling, what am I talking about? We have a cooling curve, standard way of doing this. Every cell gets, we look at the density and the temperature, and then go to a standard cooling curve. Here, I believe we're even using Delgrano-McRae, very old cooling curve. But basically, the idea is optically thin. We refrigerate that gas. And so what you see, of course, the shocks respond to this. The shocks become, they lose energy. In some sense, they become more brittle. They're more subject to various kinds of instabilities that can happen, both at the shock head and the contact discontinuity. But still, you still see now, what you see is an even more narrow jet emerging from these conditions, or these cases, than we had before, which makes sense because there's less thermal energy, there's less lateral expansion. But still, the overall height in Z is about the same. So you're still getting the ram pressure is still doing its work. Here is the temperature, again in this case, and you see that instability sort of that are forming at the edge, which is exactly what we'd expect. These are both cooling instabilities and thin shell instabilities occurring. So a lot more substructure. And now if we go to the low momentum cooling case, now you see something really interesting. Look, the bottom lobe is significantly different in size than the upper lobe. And what it really tells you is there's just there's something about how the bottom apple core formed that is making it more difficult for this material to flow out of the inner region. So I found that to be very satisfying, very interesting. Here's the thing that's really remarkable for someone who's been spending their whole life doing outflows and these kind of wind-wind interactions. Way down here, notice the size scale here, 100 AU. Down here at 1 AU, there is that conical inner shock that Vincent and Harold and I found in those totally low-resolution simulations. There's this little tiny, eyeball-shaped shock which is redirected. This is Mach number, by the way. As you can see, this is high. These are high Mach number flows, as you'd expect. The wind expanding away from the central region, then being redirected into these jets, right? So you see this very strong shock-focused inertial confinement, something we talked about 25 years ago. You get these jets, which themselves are now, they're supersonic, but they are going to expand. There's enough thermal energy in them that they're still going to do some expansion, and they will once again become they'll become hypersonic, and then form those larger elliptical shaped shocks, like here. Okay, so that was, to me, amazing, that, now factors of 100 now we're able to increase in size scale, and we see the little tiny shock-focused inertial confinement happening there. One last thing just to point out here is the asymmetries. So these plots show top and bottom lobes for the different cases, model A, B, C, and D. This is the cooling low momentum, cooling high momentum, etc. And what you see is there's really there's quite a bit more asymmetry just in terms of how far they get. Clearly, the low momentum case, one of the lobes is tiny, the other lobe is huge. this is a measure of asymmetry in terms of we looked at the cross section, how much cross sectional area there was in the top lobes, but looking at the about 1/3 of the way up and 2/3 of the way up for top and bottom lobes. And this gives you a measure that, there's the lobes, as we can see visually, the lobes look different, which is exactly what we see in the observation. So this is very, very promising in the sense that we're seeing everything come out of the common envelope evolution that we need in order to explain things that have been quite mysterious to us for and understanding protoplanetary nebula. We certainly nail the collimation, we're getting the instabilities or the asymmetries, and we're getting most of all these gross asymmetries, the possibility of that in the sense that one lobe can be very different in terms of even size from the other. So I'll end there, and I thank you very much.
Time for a few questions.
So inside the flow, you seem to have almost like sharp diamonds, look like, and not quite, but I was wondering, are those kinds of structures visible? I mean, can that explain some of the small scale structure you see in the
In some cases, it might be. M29 is an example where you really see what appears to be about midway up through the lobes. You see these brightened features. So I think, I mean, it's one. When you look at it, you're like, oh my God, that's it. And then sometimes when you look at the kinematics and such, or the ionization structures, it kind of goes away. But I think, certainly some of these things, some of that knotty structure, maybe not the shock diamonds, but the inhomogeneities that are being developing in the flow, I think those are going to be well matched to what we see in the observation.
This is really interesting. I guess you're doing this all without any magnetic fields, which is always
right.
a big accomplishment. But what I'm curious about is this wind that you introduce at a certain phase all of a sudden. Presumably, if it's a common envelope, the star is kind of peanut shaped. And why would it have a spherical wind?
Well, it's not, I mean, again, so that black box, right? I mean,
okay.
we literally put a spherical distribution around there. Maybe there's a accretion disk around one of them and it's a wide angle wind, right? If it's already a jet, case over, right? But we wanted to hear.
I was trying to make it not a jet, but something that comes from a non-spherical star.
But again, we don't really, we so much don't know what is at the bottom in there, right? Maybe it's a merged star, and there's the standard idea, for that people have been using for planetary nebula, that a post-AGB object they'll model as a 10,000 degree, star, and that it seems the spectra kind of match that, right? So for post-AGB objects. So who knows what's in there? So we're again, that's why I'm saying this is kind of an experiment, a physics experiment more than we're directly trying to match something.
I mean, it's a proof of principle that since the sphere is the worst possible case for ultimate collimation, if you put in the sphere and then you get collimation, that's
Well, that would
well, not necessarily, because if you had a peanut star, you might not get very much mass out of the poles.
Yeah, that's.
Well, no, but if that's the case, then it's still going to get redirected. You're still going to, that's the thing. As long as you're getting any mass, I mean, I think if you had something that was maximally in the equator, you still might be an experiment to do. We should try that. I still think you're going to get it redirected.
I have one comment, one question. First of all, those pressure confinement shocks and recalibration look extremely similar to jets you get from compact objects in stellar envelopes and extensive literature, and I'm sure it's the same idea there. Second of all, and Brian and I had a paper on predicting on what would be the observed temperatures of these radiative shocks, and I was wondering, observationally in these outflows from the nebulae, do you see actually temperatures where you would get it naively from those into the 5 or actually lower temperatures?
The temperatures for protoplanetary nebula before ionization, because once ionization kicks in, everything's going to be 10,000 degrees, right? But for protoplanetary nebula, where there hasn't been significant ionization from the central object, I believe you're getting temperatures at the levels of tens of thousands of degrees, which is sort of what you'd expect for for a cooled 300 km/s wind. Other people can correct me if there's any other planetary nebula observers here, but I believe that the observations, things are being lit up there by shock-excited emission. So,
Yeah, because we had a prediction that radiative shocks are actually going to be emitting at lower temperatures than do the jump conditions give you.
That's it.
And of course.
What?
If they stand, it also found this.
Yeah.
But that's, okay, yes, I mean, I would expect that as well, just because the jump condition, I mean, if you're using a gamma equals 1 shock, okay, but but in reality, of course, you know, there's actually cooling going, but you know, you have to track what's going on behind the shock. So I wouldn't be surprised that you're getting lower than the jump condition.
So Morgan, then Natasha.
So I'm curious about, in this kind of controlled experiment, it's wonderful that you know the momentum that you're putting in.
Right.
So then, have you asked yet how much of that momentum is vented towards the poles versus directed to that torus? And I think what I'm getting at is like, do we know over what time or if that torus is sort of ablated by this process?
Yeah, we haven't looked at that yet. That's actually a great question. I mean, I think the problem is that the torus is so dense. Like the polar equator contrast here is factors of thousands, you know, so that it's like really the stuff just, you know, just leaves. So I don't.
So is that saying that like almost all of the injected momentum
Yes.
is
Yes.
going to the poles?
It's going into the poles.
Yeah, yeah.
As
So we-
opposed to blocking off, and just blocking off the equator, just selecting the momentum from above, it's actually
redirecting.
Yeah.
Right, which is why I think, Stan, to your question, if you
Yeah,
had
it's
if
also-
your wind was completely in the equator, it would still end up in the
Yeah.
poles. It's got nowhere to go, essentially, you know.
I'll see.
But we should look, I mean, we haven't looked, you know, that we haven't gotten to that point yet.
Yeah.
So I have a question. So your black box with those properties, 300 kilometers per second, or in, don't remember, sort of, for temperature, to what kind of post-common envelope remnant it physically must close?
I think it's, you know, these numbers are reasonable for a, you know, like a post-AGB object, like if you're making a model of a post-AGB object, you know, climbing up the learning curve. So I think that, you know, the 300 kilometers per second or so, you know, is reasonable for, you know, an object with this kind of mass. The mass loss rates may be more difficult to get out of post-AGB object, but they are very much in line with what we see from the Bacharabal, you know, et al. Results. If you're looking at the energetics, you know, Bacharabal has looked at all of these post-AGB collimated flows, and what they infer from the observations is certainly mass loss rates like this.
Last question, Marcel.
So there's actually one more comment to Natasha, one real caveat here. So the common envelope we gave Adam is a non-ejected common envelope. So your usual 10% out, and the rest is kind of going, but it's coming back, right? So if you can get the post-AGB, well, the core, to do that wind when we eject it, which is about 3,000 days after, you know, we give it 3,000 days to get its act together, and then the fast wind goes, right? If that is realistic, which it might be, then this is what happens. But if we instead we have a situation with a longer phase, thermally regulated phase afterwards, with the envelope having to adjust, the star's not yet a post-AGB star, still an AGB star, still got its envelope, the binary is in there, so there's going to be something else happening. Then whatever 10% was ejected at the beginning is going to be gone. Whatever else is going to be more diffuse. So suddenly the shape around your fast wind at the time of initiation is going to be different. So that's actually one big unknown, and it is all related to the ejection property of the common envelope.
And that's the future of this, I think.
Yeah, that's
like look at more.
the
So we
next
took
thing.
one common envelope outcome. I think now look, you know, more broadly. Because I think, you know, messing with the initial, you know, the collimation of the interior may not be that interesting because already putting in a jet, who cares, right? But I think certainly mass loss rates, as you saw, if you crank down the momentum, you know, are you just going to bubble away? You're just going to produce bullets, which is sometimes you see, like every now and then you're going to be able to drive your way out of it. But also to see the common envelope, you know, different common envelope outcomes will provide different kinds of nozzles or no nozzle at all. So I think that is actually a place where, you know,
There is a question here. I mean, with the momentum that's put in per unit time, it's basically chosen to be like 1,000 times the radiative, 1,000 times the solar luminosity, which is like the radiative luminosity of the AGB, or that's why it's spherical. And there may be issues with the collimated momentum in some variable objects, which would suggest that you would need another source of momentum, like accretion or something. So this is limited by the maximum momentum influx from 1,000 solar luminosity.
Okay, I think we should just close on that. Thank all the speakers again. So